So next up we have Liv Matan. This is Liv's first DEF CON. How about a round of applause there? How many other people's first time here? Look at that. That's great too. All right. So Liv's a cloud security researcher at Hermetic, where he specializes in application and web security. He previously served in the 8200 Intelligence Corps as a software developer, and as a bug bounty hunter, Liv has found several vulnerabilities in popular software platforms, such as Azure, Facebook, and GitLab. In this talk, Liv's going to show what it's really like behind the scenes of cloud vulnerability research, and we'll discuss the lessons learned while dealing with the barriers and challenges that arise when searching for and reporting new vulnerabilities to the biggest cloud vendors. So let's give another warm welcome to Liv.
Thank you. Can you hear me? Good? We got it. Okay. So this is my talk, the Rocky Balboa Guide to Cloud Security Research. I'm Liv Matan, a security researcher at the Hermetic research team. I was also recognized recently as Microsoft MVR for the past year. I'm a bug bounty hunter in the major cloud providers, and I also found some cool vulnerabilities on Facebook and GitLab, so make sure to visit my blog if you're interested in seeing those. And I'm a former intelligence unit software developer. And I was also breakdancing when I was about 16 years old, so if you see me in the dance floor in Vegas, feel free to hit me up and we will dance. Okay, so our agenda for today, I will give you some unique approaches you can take for your own experience, from my personal experience, my honest experience. And when I'm saying honest, I mean that I'm gonna talk about the failures and the successes. I'm gonna show you some case studies, and I hope you will also learn some application security from those case studies, because they are focusing on application security and cloud security in correlation. I'm also gonna give you some lessons we can learn from our research by showing you the case studies. And I'm gonna wrap up by talking about the experience working with different CSPs from my experience and some takeaways you can take home. Okay, so cloud services, we are cloud people. We all know that right now the major cloud providers are offering hundreds of cloud services. And when we are talking about security research in the cloud, it can be very confusing for us when we are stumbled upon all of those services. So how would I not get into the rabbit hole of deep diving too much into my research? Or how would I even find a lead to start researching a service or a feature or whatever I want to research, right? For this, I constructed those following approaches. Don't take those approaches guaranteed. They work for me, and we will follow those approaches with the case studies I will show you in the next slides. The first one is find common ground between services. The second one is the opportunistic approach, and the third one is the laser focus on a service. Keep in mind that those approaches can also lead you and take you to other approaches, so feel free to freestyle. So the first one includes inter-service communication. When looking at those, I found out that those usually are more prone to vulnerabilities. Also looking at some management panels. Management panels usually includes a lot of services rather than one service. We will show you a case study on this particular use case. Also, it usually lets you get some vulnerabilities with an higher impact and a larger blast radius due to its nature of the common ground of a lot of services that are correlated in the process. The second approach is the opportunistic one. We are taking advantage of the hundreds of services that are offered by the cloud providers. We will make a huge reconnaissance of the services, hop between services until something catches our eye, and then we will get into the service and try researching it further. Also, we can try to look for some low-hanging fruits with this approach. The third approach is the laser focus on a service, and it includes reading the documentation of the service and deep diving into the documentation. Keep in mind that obviously you will read the documentation of the service and learn it in the other approaches also, but this one you should focus on it more, read all the features, give it a thorough review of the features that the service is offering to maximize your attack surface. So our first case study for today, a really exciting one from my personal experience, is Emoji Deploy. Emoji deploy is a vulnerability I found in Azure Web Services, including function apps, app services, and logic app. It was an RC that was resulted from a CSRF attack. To those of you who are not familiar with CSRF, I will give a brief explanation on it in the next slide. So let's start by observing Azure Web Services. Those can be categorized as logic apps, app service, and function apps. I'm sure you all know those services. Those are very popular. This is why I focused on them, because I wanted the impact to be sufficient and maximized. Each one of those services deploys the SCM panel. This SCM panel is a management panel that deploys by default in each of is deployed by default in each of those services. And it also deploys the Kudu service. This is the panel. This is how it looks like. Not very beautiful. So I started by looking at the panel, see the features of it, and I saw you can look at some processes, environment variables, you can debug the application, and it seems like a good victim and a good target to try and exploit. And this is the common ground I found, because this panel is actually managing all of the services applications that I just showed you earlier. So when starting to look at the SCM panel, I saw something that caught my eye, and this was the same site attribute of the SCM panel. The same site attribute is a browser security feature that its intention is to protect against cross-origin attacks. Some of those is a CSRF attack. And in this case, in the SCM, the same site attribute of the cookies were all set to none. It means that this protection just wasn't there. So a brief on CSRF. Let's say my lovely grandma wants to transfer money to me, her lovely grandson. So she visits the bank website, logs in, clicks on a couple of buttons, gets her session cookies. Then behind the scenes, a post request to the bank's website will be sent, and she will transfer the money to me, and I will be happy. After a couple of days, she visits the attacker's website. And the attacker's website behind the scene is sending a post request from the client side that will send the money from the grandma's account to the attacker's website on her behalf. Because the browser context was from my grandma's browser context, the request will be sent on her behalf with her session cookies. And also keep in mind that the origin of the request, the origin HTTP header, will be set automatically by the browser. So servers can potentially look at the origin and block this CSRF attack. Okay, so our mission for today is RC, and let's get started by defining origin. Origin consists of a scheme, hostname, and port. Simple as that, just remember that, okay? So as said, usually servers can block cross-origin attacks or a CSRF attack by checking malformed origins. And this time, I looked at the SCM panel I showed you earlier and tried to see if there is an origin check, because I aim for a cross-origin attack, a CSRF attack. And I tried to send the normal origin that will obviously be accepted. Then I tried to send .attacker.com at the end, at the start, and try to play with the protocol, just to get a feel of the server origin check. And they all got unauthorized. So it means that there was a check, that there was an origin check in the SCM side, in the server side, trying to block me from accessing it. What about spatial characters? With a black box research, I can assume that there was a regex behind trying to block me from sending malformed origins. And I know that spatial characters can break regexes. So I sent the following. I sent the accepted origin, then the spatial character, for example, $1, and it got accepted. But then I sent the same with an hyphen, an underscore, and both got unauthorized. And I didn't know why, because it was a black box research, but keep that in mind that the SCM just doesn't accept those two particular characters because they are very important for me in the flutter. So we tried to check the origin and sending malformed origins with a proxy. But if I send it with a browser and domain names do not allow spatial characters, how would I even register a domain with spatial characters inside? Because it should not be allowed, right? Dollars are not allowed in domain names. So then I went on researching browsers' compatibility with spatial characters. And I found out that actually browsers don't care about hyphen and underscore in the origin header, and they just send the request and pass the origin in the request. So I can maybe try to make a browser send a request with a malformed origin containing those spatial characters that will allow me to bypass the origin check. But we have a bit of a problem here, because if you are following, right now I have a scenario that browsers accept the hyphen and underscore, but the SEM regex doesn't like them. And the opposite, browsers do not accept any other spatial characters, and the SEM regex accept those. So I went on and tried the following. I tried inputting underscore as a subdomain, and both got accepted. And I could bypass it. The browsers and the SEM server both accept underscore as a subdomain, and the SEM server was spawned by an emoji. This is the name of the vulnerability, emoji deploy. This is the cross-origin bypass I had. And now we will get into the deploy part. So, thank you. So at this point, we can now force authenticated victims to do something in their SCM panel from our origin, our attacker's origin. So let's try and find a vulnerable endpoint. We need impact, we need something to exploit, right? So the SCM server is using the Kudu service. The Kudu service is open source, as I just searched the internet and looked, and it was open source. And open source is kind of fun for attackers because I can read the code and I can try to look for vulnerable endpoints. So our candidates for the day were denial of service, but we will focus on also the remote code execution that will maximize our impact. The remote code execution had an API zip deploy endpoint. The zip deploy is an endpoint that Microsoft has implemented for DevOps and IT usage to deploy zips to applications through the SCM panel. So through the SCM panel, you make a request, and the zip will be deployed to the application. And the interesting part here that the zip package will unpack at the dhome site www root of the application. So let's, for example, we have app service that is a website in Azure. The zip package from the SCM will unpack in the app service website. So maybe I can try to abuse it and upload a web shell. So mission complete. This is our recap. Victim visits a malicious website. The attacker uploads malicious zip file through the victim's browser. The malicious zip file will unpack with the malicious code. Happens to be a web shell. So web shell, to those of you who don't know, I can just control the website and run code on it. And we got a one-click RC on all of those services through the common ground I showed you. I also have a cool pre-recorded demo for you. So have fun watching it. So the victim's empty web root. You can see there was no web shell, nothing there. There will be, spoiler alert. This is the API zip deploy endpoint that I abused. This is the function of the JavaScript code that I set on my website in order to upload the zip to the victim's application from my website. It's a cross-origin attack. This is the web shell I uploaded, ASPX web shell, .NET application. And this is my website that contains the malformed origin that will bypass the origin check. The cookies will be transferred, the cookies of the victim, because the same site attribute were all set to none. The content type, it's another thing that I didn't have time to explain here, but feel free to visit my blog for the full technical details and the bypasses. And the victim has visited our website, the web shell has been uploaded, and now the attacker can go and run commands on the victim's website or application. The interesting part here that the attacker can also extract the victim's managed identity token. And this managed identity token is used in those services in order to let the services interact with other services in the cloud. And usually websites, as we all know, interact, for example, databases. So the attacker can potentially also laterally move to other services like databases by extracting the managed identity token and use it. So our next case study is the opportunistic approach. We said we have a lot of approaches. One of those is the opportunistic one, showing you free case studies on AWS Cloud Shell. One of those was resulting from a public caching opportunity that led me for 2x success on AWS Console and the Cloud Shell subdomain, and also a case study on one-click Cloud Shell OAuth token leak, and the exchange of the token failed. And I told you that I will also share the failures, and we will see what can we learn from them. Okay, so sorry, I have to drink. Okay, so AWS Cloud Shell caching mechanism. So I started by looking at AWS Cloud Shell, and I saw that it had a public cache. And in my attacker head, I thought to myself, maybe I can abuse this public cache with a cache poisoning. Cache poisoning means that I can abuse the shared public cache between users by forcing the server to return me a malicious response. And this response will be publicly cached and returned to other users. But then I saw the vary cookie header. That means that the response will be cached only in correlation with the cookie. So my cached response will not be the same as the victim's cache response. So it was failed. But it led me to finding 2x successes on AWS, so it wasn't that bad. So we start by looking at the post-message communication, and you don't need to know much about it, but the only thing that you need to know is that the window of Cloud Shell and the window of AWS Console, the windows are communicating with a post-message communication, and this post-message communication allows you to communicate between windows, and those domains are using get parameters to indicate to which domain to send the post message to. So when looking at this feature, something really caught my eye. After looking at the public cache, I tried to find a malicious input from the response to be reflected to other users and be cached. And I found this parameter, the parent origin. This is the parameter that indicating to which domain to send the post message request, as I said earlier. And I saw that there is a reflection from my user input to the DOM of the web page. And with that, I tried to inject quotation marks and the word hey, just to test the reflection. And I saw that I could actually break out of the attribute, the content attribute of the meta tag, and inject some weird stuff. But I had some obstacles. Those were the parent origin injectable parameter was a URL. So it was quite strict because AWS was expecting a URL, and URL cannot have special characters and stuff. Also, no spaces were allowed and no slashes were allowed. So my ideas were use slashes instead of spacebar, but no slashes were allowed. Another idea was use %0c, it's a URL encoded form fit character that the browser will treat as a spacebar. And this was a success. I injected the following, and I got a pretty cool XSS, a simple one. Image source equals X, and on error will pop an alert just for a POC. But it wasn't that easy because AWS Cloud Shell had a CSP. And you might think a CSP, AWS Cloud Shell as a cloud service provider. No, it has a content security policy. A content security policy is a browser mechanism that allows users to restrict their JavaScript environment in the browser, and also maybe block XSS attacks. So this time they had a CSP. The CSP can be returned as response headers in the server or just as a meta tag in the DOM. This time it was in the response headers, so I looked at the CSP and saw that there is a frame ancestors directive that was set to none. And as I know that the feature is implemented by post messages from the window of the Cloud Shell main domain to the subdomain of Cloud Shell. And when they are communicating, it happens by iframing, by the main domain iframing the subdomain of Cloud Shell. So I was expecting to see the subdomain of Cloud Shell or the main origin. Then I had a bypass idea. maybe try to inject the following. I can maybe try to input some malicious spatial CSP directives that will allow me to bypass the CSP. So my bypass idea was this. I injected the following two spatial CSP directives that Garrett has discovered that can override other CSP directives, and the XSS together, and I got blocked again. It was failed. It was failed because the browser was telling me that spatial characters are not allowed in a CSP. And the server there was parsing the form fit character I injected earlier in the response headers different than he was parsing it in the body of the response. This is why the browser was just seeing the form fit character as a literal form fit character and not as a decoded form fit character that the browser will treat as a spacebar. So a recap on the XSS on Cloud Shell subdomain, and CSP bypass attempt failed. And another main domain, XSS on the main domain, a different CSP, script source SHA-hash. We don't have enough time, so I will just make a blitz on it. So this is me fighting AWS CSPs. The script source hash gotchas. The script source hash is basically matching a script content to a hash. If there is no match, then the script just won't run. This is a CSP feature. AWS used the dynamic hash generation. The hash is generated also from my injected script, so there will be a match, and the XSS will be executed. So another XSS after a lot of bypass attempts, I came up with this payload of arithmetic operations. But when talking about impact, this CSP also had a sandbox, and this sandbox wasn't allowing me a lot of impact. So, unfortunate. Another case study of AWS Cloud Shell of token leak, continuing to research AWS Cloud Shell. And the Cloud Shell authentication works as follows. The STS can be omitted. The only authentication that works here is session cookies of the user. So the user is visiting Cloud Shell subdomain. Then in return, he gets the script embedding to the auth subdomain. And he gets, in return, a dynamic callback JavaScript that contains the sensitive auth token of the user, the session token. This is the script. This is how it looks like. And the red flag here is that scripts are allowed cross-origin. Origin A can embed script from other origins. How much time do I have? Sorry. OK. So the attacker's opportunity here is to lure victims into his website, force the Cloud Shell authentication through the script embedding, then gets in return the callback.js script in return to the cookies of the victim, another cross-origin attack. But how would I read the session token of the victim with JavaScript? Because the function here doesn't have a name. So I had to try and abuse it with some logic bypasses. And I came up with a prototype pollution bypass. This is the breakthrough because I can, because I control the website and it's a cross-origin attack, I can prototype pollute the ends with function and bypass the origin check that was on the JavaScript, and also hook the post message function to fetch the code to me. Another pre-recorded demo, but we don't have time. So there was another disappointment here because AWS actually had an IAM layer that restricted me from exchanging the stolen token. And this is an internal guardrail IAM layer that I found out that AWS had on Cloud Shell. AWS also didn't fix this bypass because they said it's not a security concern and it requires user interaction, one click. So this is a recap for the leak. So lessons. We learned about Cloud Shell internals. We learned that one layer of security is never enough. XSS, CSP, and prototype pollution, technicalities, and internals. We learned a lot about them. And the thing about one layer of security is never enough is a really cool lesson, because if the IAM layer just wasn't there, I could override victims' Cloud Shell sessions with just one click. So time, sorry? OK, so our next case study and the last one is laser focused on a service, uncovering free Azure API management vulnerabilities. We'll focus on just one vulnerability, and this is an SSRF one. An interesting backstory here that taught me a lot about reporting vulnerabilities in bug bounties is that this vulnerability was first reported to Microsoft by another cloud security company. After a couple of days, it was fixed by Microsoft. After a month, we reported our findings, and after another month, we saw that the blog post of the other cloud security company was posted. And we saw that they posted the vulnerability we reported. But then I tried to reproduce my vulnerability, and it was still there. So it was actually a bypass to the vulnerability the other cloud security company reported. So the thing that got my attention is this feature of Azure that lets users retrieve schemas from external resources. And this is how it looks like behind the scenes. It was sent through an HTTP header, and I tried to send localhost to try to force the server into sending a request to localhost and returning me the response, an SSRF. And I got forbidden. Then I tried to send localtest.me. It's a domain with a DNSA record to the localhost IP address. And I got not found, means I bypassed the protection that was there. Then I tried to access some internal services in some ports. For example, 30, 300, 3000, etc. And it all got forbidden. So I found out that there was a regex as another defense layer on the server. And this regex was especially and specifically for those ports. So it means that they might contain some internal services that Microsoft just don't want me to see. So the main bypass was from the Azure portal, we input our redirect server. Our external redirect server will obviously won't blocked because it's a redirect server that Microsoft just don't care about. Our redirect server will forward the request from the cross proxy that is sending a request behind the scenes to the internal services, and we got a bypass. We could access internal services. Also, we could access the API and management Kudo server that now you know the Kudo server and what it's capable of after the emoji deploy example. But the interesting thing here that I tried to access IMDS, and I got blocked because of the X404 header that is preventing me from accessing it. But it led me to a research on IMDS security that I presented at the latest Ford CloudSec conference. And there are more blogs to come. So we learned something from it. And also, we learned a lot about the API management reach features because I followed the approach of reading all the features and trying to learn about the service. And also, I learned that the CSP IMDS X404 header protection is influential, and it blocked me from accessing the IMDS. We'll wrap up by speaking about the experience working with different cloud providers, about fixing vulnerabilities. As we saw, some cloud providers prefer to fix vulnerabilities and bypasses that might not wreak a lot of impact, but they will in the future because an attacker could possibly bypass the other layers. And some just prefer to fix those. About bounties, cloud providers have a lot of bug bounty programs, and we as a community encourage those bug bounty programs, and they encourage us in return. About the openness with the community, I found out that some cloud providers actually try to avoid publications of vulnerabilities. And some cloud providers are very open, and I really encourage it because it can prevent breaches in the long term. About the time to answer, all the cloud providers were really fast with, in regards to answering reports, and it also works in correlation with the security team size. So takeaways, non-impactful research can lead you to many interesting places. Embrace losses. Don't be afraid to try silly ideas. And the cloud vulnerability research role is different, so take care. Thank you, guys. Whew, I didn't have time. Thank you.
If anyone has any questions, you want to meet them outside?
Yeah, you can meet me outside if you have any
questions.
questions.
Thanks so much for coming, folks.